thanks, Patrick, for the introduction. My name is Chandra, and I am a principal researcher at Certora. If you want to know more about Certora, we have a booth at the back. And today I'm going to talk about crowdsourcing specifications, or proactive security. And I must say, Kurt actually set me up perfectly, because a lot of the stuff that I'm going to talk about is very similar to what he mentioned in the previous talk. And the only difference is I'm going to talk about specifications, and he was talking about testing. And so this talk, by the way, was originally intended to be given by my colleague Nurit, but she wasn't able to come, so I'm representing her. So I think everybody in this room is pretty much convinced that formal verification is quite useful for DeFi. And there are some nice properties about DeFi that make it more practical to use formal verification in this domain. One of the things that's nice about DeFi is that the programs are usually not that big, and so formal verification scales better. And on the other side, though, the code for a lot of DeFi applications can often be quite complex. So it also poses interesting challenges for formal verification. So just to give you a quick overview of how formal verification works in this domain, usually you have some contract code in Solidity or Viper or any other language, and you have some specification in some declarative specification language. And you give it to a verifier, and the verifier tells you either that the code matches the spec, which is great, and then you can go and deploy your contract, or it actually finds a violation, and you can look at the violation, you can fix your code, and then you rinse and repeat until you get the green check, and then you can deploy your code. So this is fine. So the only downside here is that writing specs is actually really hard. And writing a complete spec is probably pretty much impossible, at least in the first chance, right? So even if you are spending a lot of time and a lot of energy coming up with really good specifications, it's almost always the case that there will be some gaps in the spec. So in this talk, I'm going to propose this idea of gradual specification. So as in the previous talk we heard, even for testing, it's rarely the case that you're going to have a complete test suite that catches all the bugs. So the same thing happens for specification, right? So what we have done is we've introduced this idea called spec bounty. So it's not a bug bounty, it's a specification bounty. And the idea is that this lets you, and by you I mean the community, gradually improve your specification over time. So as t goes to infinity, hopefully you're going to have a much better specification. And so how does this work? So we start with a reasonably good spec. It's a best effort specification. And then we try to evaluate the specification based on mutants. So what are mutants? These are intentionally injected faults in the code. And we want to see if these faulty versions of the code are caught by the specification or not. And if it's not caught, well, then that's a hint that maybe we can add a specification that can catch those new mutants. OK, and so why does this work? Well, there are two reasons we think that this is a good idea. First of all, if you work on some specific protocol, it's often the case that the things you learn and the kinds of properties you write, they actually do transfer to other protocols, right? So it's not like when you write a property for one program, it has nothing to do with anything else. Like you learn from that, and you can apply those ideas to other protocols. And the other thing is that the longer the protocol is around, the more wisdom you gain, right? So people use the protocol, you learn all the the potential bugs or vulnerabilities it can suffer from, and you can use that information to improve your specification over time. So these are the two reasons why we think that spec bounty is an interesting idea, and it gives us a way to engage the community to improve our specifications over time. OK, so I'm going to give an example here. So this is a simple example. It's a contract called Borda. So Borda is a voting mechanism. And you don't necessarily have to read the code and understand exactly what's happening. But the main idea is that there is a function called vote. And it takes 3 addresses, first, second, third, and it just assigns votes to them, right? So it assigns points to the 3 addresses. So what are some interesting properties about this that could be worth checking? So I have a couple that we wrote here. If you have others, feel free to speak up. So I'll tell you some of the interesting properties that are important for Borda to satisfy. So one is that every voter should be only allowed to vote once. That makes sense, right? We don't want to have too many votes from the same person. We should make sure that the votes are, the points are correctly added up so that there is no mistake. We also want to make sure that the winner has the largest number of points. That's an obvious one. A subtle one is that the order in which you vote should not actually affect the outcome of the voting. And finally, another property is that everybody should be allowed to vote. So if you have not voted yet, you should get a chance to vote, and no other address should be able to prevent you from doing so. Okay, so these are some properties that we wrote, and we actually have a mutation testing tool. So we use the tool to generate some mutants, and we actually even got a 100% mutation score. So we were really happy. We were like, this is the best specification we could have written. There's no loopholes. We're good to go. But then we were like, is that really true? Like, did we really actually cover all the cases? Because at the end of the day, mutation testing also uses heuristics, right? So how do you know that you have all the mutants that could possibly be relevant? So to answer that question, we actually did a challenge. So we basically said, we announced a challenge to the community. We said, if you can find a bug in this contract, given some constraints, right? So you can't change the interface and so on. If you can find a bug, and if you can come up with a spec that catches the bug, you will get a reward. And we have, you can see the details of the actual reward over here. And what we found is that there were lots of mutations that our participants found that mutation testing couldn't find, and they actually led to new specifications being added to the spec. So just to give you some examples of what these mutations look like, here's one that somebody wrote. Basically, what it's doing is it's just saying, in case there is a draw, the outcome of the vote can change. So this is bad, and we don't want this to happen. Here's another one that we thought was interesting. So here, the order in which the votes are being given to the 3 addresses, first, second, third, this has been changed. And it turned out that this also affected the result of the vote. So this was also bad. And here's another one. This is a kind of an interesting one, I would say. So somebody just added another function to the contract called switch winner. And they basically, straight up just changed the winner by assigning winner to, the new winner to the winner variable. And this also changed the outcome of the voting. So these were some interesting mutations that the community found, and then they were able to add more specifications that could catch these mutations. So we were quite excited about this result, and so we decided that we will continue further. And this time, we did a similar kind of a contest, but for AaveGo. So we announced the contest. You can see the details about the contest here. And the contest ended on 15th of October. So we are still kind of working on putting the results together, but we already have some early results that I'll share with you. So what we want to show here is, I just wanted to give you some examples of mutants that were easier to catch and some that were not very easy to catch by the community. So here's an example of a mutant. I hope that this is audible. I hope this is visible, but if not, I'll just walk you through the important differences. So here, the change that was done in the code is there was a require clause, and we basically just changed the thing that the require was checking from equal to 0 to just being, greater than 0 to being equal to 1. And we found that this mutant was caught by only 1 participant. Like none of the the remaining 9 participants could not write a property that could catch this mutant. Here's another one. In this case, what we did is we just changed the code to remove a role from the function. Right? The function body doesn't actually matter. The main difference that is important here is that we just removed the only owner part from the top of the function declaration over there. And it turns out that this was actually easier to catch. Apparently, 5 people were able to write a rule that would catch this one. Here's another one. This is similar to the first one we saw, where instead of checking greater than 0, we were checking it equal to 9, some random number that we just picked. And this was also really hard to catch for some of our participants. Another one that we thought was similar to the second one, here again we changed the role. So we changed the signature of the function, and it turns out that this was easy to catch. Same here. This mutant is similar, and it was easier to catch. This one, on the other hand, changes the logic, so it adds a new require statement in the code, and this was actually hard to catch for the participants. And finally, this is the last mutant that I'm going to show, where again, we actually changed the code in some meaningful way, where basically we changed the assignment to filter the facilitator.bucketCapacity to just be 0. And so it turns out that this mutant, for some reason, was easier to catch by most of the participants. So this experiment kind of led us to believe some things, and I just want to share what our observations were. So one thing we found is that on average, it's actually easier for, harder for the participants to catch logical mistakes. So by logical mistake, I mean things where you change some logical operator, or you change the semantics of the program in some meaningful way. These are really hard to catch. We also found that if you have a mutation testing tool, that is actually really good, but that's not sufficient. You need also to have manual mutations that a programmer writes, because you do need some more domain knowledge to come up with meaningful mutants that can actually expose problems in your specification. So I think that those two things together is what you really need to be able to assess and improve your specs. So what now? Our next, the thing that we want to do after this is we don't want to have any time limit. So remember, this one we actually finished on October 15th, but our vision is to not have any end date on these spec bounties. So it would be like a real bug bounty where you can just write and submit a specification whenever you want. And by doing this, I think over time, we're going to have much better specifications. And so finally, I just have a couple of points that I wanted to share in terms of the lessons that we learned and things we can do better. I also want to hear if you guys have thoughts on any of this. So writing specs, as I mentioned in the beginning, is actually hard. So not only it's not like bug bounty, right? Like you don't just find a bug and just report the bug, right? You have to learn how to write the spec. You have to write the spec. You have to show that it's good. So how do you incentivize this? This is actually a really hard problem. So one of the things that we always encourage the participants to do is to submit as early as possible. Because if you submit early, then the people who are going to submit later cannot submit what you submitted. So it's always harder to, the longer you wait, the harder it gets. So you should always submit your specs and your bugs as early as possible. You have to demonstrate that it's actually an interesting mutant and an interesting property. And by that, what we mean is that the mutation should not be caught by any of the existing specs, right? So if it's already caught by some existing property, that's not really interesting. And same thing for the property itself. It should not have an overlap with existing properties. So it should capture some new behavior of the program. So for example, for the Borda one, all those mutants that I showed, they were actually changing the behavior of the code in a meaningful way. And in that case, it was basically changing the outcome of the vote. So that's why those were interesting mutants. And another thing that we found is that this was actually from the Aave experiment that we did. It's actually important to understand what mutants are easier to catch by participants and what mutants aren't easy to catch. Because at the end of the day, if the mutant is impossible to catch, that's not interesting. But if it's really easy to catch, that's also not very useful. So you want to have the right balance between what kinds of mutations you want. We also saw that based on the Borda experiment, people actually submit two types of mutants. One is an unintentional bug, right? Like it's a mistake that anybody could make, and the mutant is just capturing that kind of a bug in the program. Another kind of mutant is malicious code, right? So this is basically, it's not really a bug anyone can introduce. It's someone intentionally trying to do something bad to the program, and you can have mutations that can actually capture that. And so both of those things are actually useful. In our experience, if it's a standalone protocol that you want to verify, you usually want to look at unintentional bugs. But if it's a new standard, for example, if it's a new ERC or something like that, you also want to take into account malicious code type mutations. And one of the things that we have found quite hard, and I just want to end the talk by sharing this with everybody else here in case there are other ideas. So at Certora, we have invested a lot of time in grading and evaluating and assessing specifications. And it's actually really hard to do it properly. So there is this question of like, is it possible to have some kind of an autograder for specifications? And if there are ideas or thoughts about that, then I would love to hear them. And I'm also happy to talk more about how we do it at Certora. Thank you. Oh, also, I should mention one quick point. Tomorrow we have a workshop that Johannes and Armin are going to do. So I strongly encourage you to show up to that and learn more about mutation testing, Certora Prover itself, and how to write good specifications and things like that. Now, really, thanks.